year's not over. It can always get hotter.
In Alabama, my first year here, they had a bank, it's called Colonial Bank downtown, they had a thermometer. And I remember driving by there, I think it was 103. Like 1985 in Rapids, or 1986, that was unbelievably hot. Morgan Riley, Brandon Jaden Gibbs, Xander, David, or I'm sorry, Daniel Ramirez, Drew Pritchett, Lauren Trent, Lance Michael Kimball, Riley, Alan, did 2, 4, 2, 4, 6. This is bigger, a larger number of people than I thought. Anyway, I put the solutions up. Did you all see them? And your grade should be on one. They should be. I'm sorry, I can't. Let me just say this. The entire exam, the way I make these exams up, I go through the quizzes, the homework, and what especially we talked about on the board. And that's how I create all these things. I don't do this, just out of the blue or anything. I do reference older material that I had, previous homeworks, exams, quizzes, and stuff like this. But I usually modify them to a point at least. Did want to say one other thing about this. I think some of the confusion may be due to a lack of actually carefully reading the problems. And I want to talk about this just for a second. If you look at problem 3, you have exp to the minus 2 absolute value of x. Now, I assume you understand that can be from minus infinity to plus infinity. There's no u of x there. There's nothing like that. So with something like that, I don't know I think I gave you a problem like this. Matter of fact, I'm sure I did. But when people go through there quickly, they think it's only for positive x from 0 to. You have to read these things and be sure you know what's being said. The problem, I really am not sure about this, but I think that problem gave people the most trouble of all of them. And I thought, in my opinion, it was very straightforward because it was just a two-sided, it was a simple exponential distribution. All right, with that in mind, I said, you can't really start a whole lot of them between 2, 4, 6, 7. But we might as well at least go over this, and if you have questions, we'll address them. So for the first problem, and I'll go through it kind of quickly, because I think everybody, you got the solutions. Did everybody feel comfortable with the test? All right. The material was meant to just reflect what we studied, what we covered. There's nothing, as far as I know, there's nothing in there that was in any way, shape, or foreign to you. And your calculators, if you want to, you can brute force a lot of these calculations, the mean value, all that stuff. But when you have an even function like that, e to the minus 2 absolute value of x, and I asked for the mean, or the average value of x, or the mean value, well, if you multiply that by x, it becomes an odd function. X times even is odd. If you integrate that from minus infinity to 0, so you don't even need to integrate it, but you can. All right. Anyway, for problem 1, this is the earn problem. So we're going to have earn 1, earn 2, and then we have the number of blue, and I don't remember this, red in each. And for earn 1, can you just tell me blue, red here? 7, 3 or something like that?
Earn 1 is 4 red and 6 blue.
And this?
Earn 2 is 3 red and 7 blue.
So there's 10 in both cases. With me, class? Now, with that in mind, if I looked at this one, if earn one is selected, or really, one other thing, the probability of U1 being selected, is that 75% or 25?
Earn 1 is 25.
All right, okay. And now, let's see, I think everybody gets the idea. This is going to be something where if they want the probability of a red selected, probability of a blue selected, we'll go through this quick. Probability of a red selected is going to be equal to probability of earn 1 times the probability of a red given earn 1 plus probability of earn 2 times probability of a red given earn 2. So probability of earn 1 is 0.25. And then the probability of a red given earn 1, for that one it's going to be 4 over 10. Both of these have a total number of 10. I can put it here. So probability of a red given earn 1 is simply going to be 4 out of 10 plus probability of earn 2, which is 0.75 times probability of a red given earn 2 is going to be 3 out of 10. And that's going to be the probability of a red. And then probability of a blue is going to be 1 minus the probability of a red. And do you all agree with that? You can do this business again to get that, but either way you get the same answer. I don't remember what they are, but what is this one?
The probability of
Red.
red,
Yeah.
0.325,
Probability of blue?
0.675.
I'm not sure about this, but I think almost everybody got this one right, I think. I wish I kept stats on the individual problems, which I was happy about. All right, so what's the first question?
You mean
They asked for, what's the first thing they asked for?
it was the probability of a red.
And then is the probability of blue?
Mm-hmm.
And what's the next?
Probability that it's earn 1 given that a red was pulled.
All right, probability of earn 1 given what?
That it was red.
Okay. And that is going to be, pardon me?
Bayes' theorem.
Yeah, so what is it going to be? Probability of?
Red given earn 1. It's the probability of earn 1 divided by the probability that it's red.
Everybody with me on this class? It's straightforward. Yeah, I don't recall anybody having trouble with this. So, probability of red given earn 1 is
4 out of 10.
4 out of 10. And probability of earn 1 is, I'll just put 1/4, okay? 25%, right? And then probability of a red is 0.325, and I don't know what that is, but can you tell me?
0.3077.
0.3077?
Yeah.
I think that's right. Another one? Another problem? It's another
The
one.
probability that's earn 1 given that it was blue.
And it's basically the same thing, only one blue, so probability. And I don't know what that is, but can you just tell me?
2 nines.
What is it, 3 nines?
2 nines.
2 nines. Okay, that's fine. Is there another part of that?
Yeah, and then it does earn 2 probability that it was red, and then earn 2 given that it was blue. for like the next two questions, sorry.
Probability, say it again?
Probability of earn 2 given that it was red.
And what after that?
Probability of earn 2 given that it was blue.
Okay. I'm just literally, this formula, the only thing I'm doing is replacing the blue with the red and earn 2 with from earn 1. That's the only thing I'm doing. I don't remember, what does this come down to?
0.6923.
And finally for this one, because it's literally the same thing, the only thing I'm doing is instead of red, I'll have blue here. Maybe I can put that, so I have probability of blue earn 2 minus probability of earn 2 over probability of blue, and what is that?
7/9.
I'm going to ask you too, next time we have a test or a quiz or anything, I'm going to ask you to give me the decimal form, not fractional forms, because I got some wild fractions. And it's like, I can do the calculations too, but it would save me a little time grading. And I'll be clear about it on the exam. Any questions about this problem? Wasn't meant to be in any way, shape, or form difficult. Next one is a switch one. And I think it's the only comment about this. Sometimes you have to carefully redraw things. That was the only problem I could see as far as the understanding. Now, there are a couple people that really didn't know what they're doing, but for the majority of you, you understood what was being asked, and you understood if they're in series, the probability of operation is multiplied. If they're in parallel, what you end up doing is having to find the probability of failure of each and multiply those, and then take that from one to get the effective probability of a series element replacing them. I got one comment too about something I would be ready for in the final. So for this one, let's see, we had a sender here. And then you had a link. And then, as I recall, this and this. And then this and this. And then you had this. And I think this was A, B, C, D, E, and F, if I'm not mistaken. Is that correct?
C is in the top right, where D is.
Okay, sorry.
C and D. That's what
All right. B. Now, correct me if I'm wrong, this was 0.5, is that right? And this is 0.5? This is 0.5? This is 0.25? This is 0.25? And this is 0.5, is this right?
Yes.
Okay. Those are just the probabilities of them operating correctly. So for the whole part of this one is just drawing the circuit right after the statement's made about what's working, what's not. So for the first part, it says what? If F is not working, isn't that right?
F is working.
Oh, it is working, okay. So F working. And that means you have really 0.5. And then you're going to have 0.5, 0.5, and then 0.25, 0.25. That would be a circuit. I'm showing the probabilities of them operating correctly, correct, everybody? So the next step is just reduce the circuit complexity, but I want to tell you what I want you to be ready for. I want you to listen. If ever there's a situation where you're going to get another one and another one You need to know how to do that. Did you hear me? We're gonna cover it right. In other words, I'm not gonna show it right here, get a little busy, but if you had something where you had two in parallel, then 3 in parallel, then 4 in parallel. I'm gonna do it right now, and then I'll get back to the problem, because I think everybody understands this one. You all with me? Now, how do you do that one? I'm just gonna ask you a very reasonable question based on an extension of logic.
Just do the same thing, just with more components, right?
Well, what you need to do is find the probability of failure of each one of these first. It just happens to be 0.5, which is nice. Follow me? Each one of those fail at a rate of 0.5. Their success at 0.5. If it was different, you would have to manage it, okay? Now, if that's the case, then the probability of failure of the entire system would be 0.5 to the 4th power if I had 4 in parallel. You all follow me? Now, the probability of it working would be 1 minus that. Everybody got that? I didn't cover it, but I want to make sure you can extend this logic and do this. That's real important, that you be able to do something like this. And, well, I'm saying that for a reason, because I'm thinking about the final exam, thinking about what types of questions I might create. And something like that's reasonable if you understand what's really going on. Now, I'm not going to ask something where you're going to get a ridiculously complicated circuit that takes too long, but something with like maybe at most 10 of these legs, 10 of these little connections that you would have to be able to more or less reduce to a single circuit to find the probability of working or failure. Anyway, for this one, now I'm going to reduce it. I'm going to take these parallel elements. I'm going to get one circuit. So this is still 0.5, the first link A. Then this is going to be replaced by a link that's going to be 1 minus 0.5 squared, because that would be the probability of that working in series. Does everybody follow me on this? Same with this one, and it's in series. And that's going to be 1 minus 0.25 squared, and that would be the probability of that working. Do you all agree with that? So the overall probability of a sender being able to send something to the receiver for this one would be, I'll call it P of A, first one. What is it?
0.164.
Mhm.
Yeah, I think that's right. That's first part. Second part was, go back to this, now what happens? Just, what fails?
C fails.
C and what?
Just C. C isn't working.
All right, so I'm going to erase it to make it clear. And if C is not working, I'm going to redraw. But I think everybody sees this. I think there were some problems with the redraw here. I don't remember who made the mistake. So if you look at this, from this point, you got a series network here in parallel with this, and then a series network here, correct? So just on the redraw here, to make sure. Start off and you got link A, and that's still 0.5. But now you got something where you're going to have a series of 0.5 and then 0.25. And it's in parallel with something that has 0.5. And then it's in series with 0.5, I think. Oh, I'm sorry, 0.25, not that.
The one in series on the top is 0.5 to the 0.25.
Isn't this 2.5 and 0.5?
This both 0.5. Right.
Oh, you're right, yeah, it is 0.5, not bad. You're right. Okay, Now to reduce this, I think I can do it right here. This is the only element. I'm gonna get it down to 0.25 first. You good with that, everyone? Then now, probability of this not working is going to be 1 minus 0.25. Probability of this not working is still 0.5. So the probability of it working right here would be 1 minus 0.75 times 0.5. And then here, it's going to be 0.25. Can you tell me what this is, by the way? Just so I can write a number down for everyone.
Talking about the final or just that
Just
part
that
of the
middle segment. You got 0.375, 1.625, right?
Mhm.
And then for the whole thing, 0.5 times 0.25 times this is going to be what?
0.0781.
0.781?
Yeah.
Okay. That's the second part. Third part. What's the third one?
C and D not working.
Oh. C and D not working. Now this one, if you did the redraws, it's hard to mess this up. This one's all series, right? So it's just going to be 0.5 times 0.5 times 0.5 times 0.25. I might as well just put that down. So you're going to take 0.5, 1, 2, 3 cubed times 0.25, and I don't know what that is. You can tell me.
0.03125.
0.01.
3125.
Okay. And the next part is what? I mean, is everybody okay with this? I can move. What's the next part?
It works from, just the whole thing works from.
Oh, everything.
Mhm.
All right, finally, probability of everything working. And that one, so the whole idea is we first turn that off and then we turn it on and we go ahead and do this. So the probability of the whole thing working, we'll call it PD, is going to be equal. So the probability of F not working, which is 1/2. You mind if I just write this out? Because you've got this. And then it's the probability, if F isn't working, of, we didn't calculate that, did we? If F isn't working, the probability that the system works, we didn't do that one, I don't think. Right? So we'll do it right here. So this is going to be what's needed for that. So that's going to be, the redraw would be equal to A would be 0.5, and then you would have 0.5 times 0.25. Now that's working. And then 0.5 times 0.25. And that ends up being equal to 0.5 times, and then you're going to take the probability of this not working is 1 minus that, same down here, 1 minus that, that's probability of it not working. So the probability of it working is going to be 1 minus quantity, 1 minus 0.5 times 0.25, and it's going to be that squared times that. Really what I'm trying to do, the redraw on this is basically going to have these two in series, and both of those two series elements are in parallel. That's the only thing I'm trying to show you. What does this come down to for this part?
0.1172.
0.11?
Yeah, 1172.
Is that right?
I got zero, for the whole thing, I got zero.
No, I mean, this part right here.
Is that not for the?
I'm not sure I put it all.
That working
like
part?
in one thing.
Well, I'm just looking at this.
Yeah, it's 0.1172.
All right, I'll trust it.
Yeah.
All right, so anyway, that's if it doesn't work. So the probability it doesn't work is 1/2. That's the probability, if it isn't working, of the system working, which is 0.1172 plus probability it works, and then that's the parallel combination, and that was from 1 plus, what was that?
0.164.
And what's the whole thing?
0.1405.
Everybody good with that class? And it's just redrops. There were really 4 redraws you had to do. But that was that one. It wasn't meant to be hard. I don't recall what the split is on these as far as the number of people who got it all. By the way, in every one of these things, somebody got it all right. And I mean, in every problem, there were at least 3, I think it was over 4 more people that got the problem right on every one of these. So I don't know any problem here that really caused a lot of people trouble. So the next part is the double-sided density function. And for that one, I give you a density function f of x is equal to e to the minus 2 absolute value of x for all x, correct? Now, I'll tell you this much. I didn't do this for a reason. I could have put down an a in there. Y'all follow me? And you'd have had to calculate that. Everybody with me on this? So that would be a reasonable thing for me to ask you. The problem is if you get the A wrong there, everything else is wrong. So that's the reason I put, or I allowed that. You okay with this, class? All right, what's the first question it's asked?
Probability that x is greater than 2.
Now, some people just assumed a one-sided probability density function, not two-sided. But there were a lot of things that went on that, actually I didn't know what some people were doing. But this is straight. You got the density function, you go from 0, or it says greater than 2. You go from 2 to infinity of the density function, e to the minus 2x dx. You don't need the absolute value because x is positive at that point. I think at least one person, I can't remember how you did this, but you integrated also from minus infinity to 2. Like you took both sides of that for some reason. That wasn't in the statement of the problem. It was just x greater than 2. And for that one, if you want to, you can integrate. You get 1/2, and then it's just going to be e to the minus 4. And that should be the right answer. When you integrate it, you're going to get minus 1/2 e to the minus 2x evaluated from 2 to infinity. At infinity, it's 0. At 2, it's going to be e to the minus 4. Follow me, class? And what is this, by the way?
0.009158.
009158. That answer I gave you full credit for any kind of fractional, anything like that. But that's the first part. What's the second part?
Probability that x is between -2 and +2.
You can do it a bunch of different ways. I mean, what you can say is, well, the probability of x greater than 2 is the same thing as the probability of x less than minus 2, area-wise. Do you agree with that, class? Just listen to the way this guy. Do you all agree with that? So if you take 2 times this answer, you'd have the area from 2 to infinity and from minus infinity to minus 2, correct? If you took that area just take 1 minus that total area, then you would get the right answer. It's one way to do it. That's the way I was thinking people might do it. So if you took 1 minus 2 times that, you would get the right answer. Do you all agree with that, class? Did anybody do it that way in here? Did you? Or no?
Well,
You're not paying attention.
no.
Do you have your test?
Yes.
Don't worry about it. Somebody did it that way, I believe. I think I know who. Anyway, don't worry. Anyway, for that, it's obviously going to be 1 minus e to the minus 4th. Did anybody put that answer down? For some reason, I think people did. Didn't you leave it like that, somebody? Yeah. Okay, that's one way to do it. What's another way to do it?
Integrate from negative 2 to 2.
You can go from minus infinity to minus 2 of e. Now it would be 2x, right? Because your x is negative, so you would have that. It would be dx plus the integral from 2 to infinity of e to the minus 2x dx. That's sort of the brute force way. You would do it that way, right? Or I should say, wait a second.
It's 1 minus.
1 minus this, sorry. You would go, my bad on this one. It would be the integral from minus 2 to 2 of, but you're going to have to break this integral up unless your calculator has the ability to do an absolute value. And it would be e to the minus 2 absolute value of x dx, which means it's going to be the integral from minus 2 to 0 of e to the 2x dx plus the integral from 0 to 2 of e to the minus 2x dx. And if you take either this one or this one and multiply by 2, you'd get the area. Do you agree, class? And what is that value?
0.9817.
Can somebody do me a favor and just do this calculation? If you got a calculator? Because I know people did that. I just don't remember. I want to make absolutely sure that's correct, and I think it is.
It's about the same.
It is the same, actually. Mathematically, I mean, you could take that out more decimal places, but they are the same. All right, that's the second part. What's the third part? Part C? Part C?
X is greater than 0. Given x is greater than 0, what is the probability that x is between 2 and 3?
All right, so given x greater than 0, probability x greater than 2 to 3?
Yes.
All right, now this is conditional. So the whole thing here that's going to be the integral from 2 to 3 of the density function, e to the minus 2x dx, divided by, and here, since we're assuming x is greater than 0, you're going to have to integrate that from 0 to infinity of e to the minus 2x dx. I'm going to make a comment here. Most of you realize that this has to be 1/2 because it's symmetric. E to the minus 2 absolute value of x has the same area from minus infinity to 0 under the curve as from 0 to plus infinity. So it's just going to be 1/2. So then you get the integral from 2 to 3 of e to the minus 2x dx divided by 1/2. And that's going to be 1/2 e to the minus 2 minus e to the minus 3 divided by 1/2, or simply e to the minus 2 minus e to the minus 3. Wait a second. Sorry, that should be 4, and that should be 6. My bad. Do you agree with this, class? All right, now I don't remember what this is, but if you left it like that, it's fine, but
0.0158.
any Y'all agree with that, class? Is there another part?
Of the main funding.
That was the thing I alluded to in the beginning about if I want, I guess this is B, the expected value of X. Well, it's really going to be the integral of X e to the minus 2 magnitude of X dx from minus infinity to infinity. Now, I tried to point this out. X is an odd function. E to the minus 2 absolute value of X is an even function. Even times odd is odd. Odd integrated from minus infinity to infinity, or really from minus a to a, will always be 0 if it's an odd function. Do you agree with that? Y'all with me on this one? Okay, so that's 0. And I think that was it. If I asked you the second moment, what would you do?
Integrate X squared. using X.
Yeah, you would. That'd be an integration by parts, I think, right? I mean, your calculators can handle it, I think, right? Okay. All right. So that's that problem. Finally, last problem was the, I took that problem right out of the book. And I changed one thing, I believe. But it was literally out of the book. So I'm trying to make sure, on a quiz, you had a problem almost like that, almost identical. Do you all remember that? I'm gonna ask a question. Are there thunderstorms this afternoon? Usually students are the ones that know this better than I do. Or is I'm asking.
I simply get rained on.
You guys have class Thursday, anybody? Are y'all heading out there? Heading home?
Probably Thursday afternoon.
Okay. I hope you have good weather for the 4th of July week. I have concerns. With all this heat, we might get some severe storms coming up. Okay, for problem 4, this is one of those things where you're going to have a current source, and then you're going to have a resistor. And this is 4 pi ohms of resistance. And power is equal to R times I squared. So it's really 4 pi I squared. And then, let's see, I is Rayleigh, right? Rayleigh distribution. And that means Fi of I looks like I over sigma times exp to the minus I squared over 2 sigma squared, and f of I, and this is probability of I less than, or I should say small I, less than some given big I, is equal to 1 minus exp to the minus I squared over 2 sigma squared. That's sigma, of course, is the Gaussian. And then let's see, the expected value of I, the mean value of I is equal to square root of pi over 2 times sigma. And I think I've got all the information off of that one up here. Now, I forgot what is this equal to 2? Don't remember.
Yeah.
Okay. So 2, and that means that sigma is equal to 2 times square root of 2 over pi, and sigma squared is equal to 8 over pi. And then from that point on, what do they ask?
The mean value of the power dissipated.
All right, so they want the expected value of the power dissipated, or the expected value of R times I squared, and that's going to be equal to 4 pi times the expected value of I squared. Do y'all agree with me there? Now, this is one of the things with the Rayleigh, do you remember with Rayleigh distribution, it was the mean squared value was 2 sigma squared for the maximal Boltzmann distribution. The mean squared value was equal to 3 sigma squared. Do y'all remember that? Back when we, how many do? I'm curious.
I remember the 2 sigma squared.
Pardon?
I remember the 2 sigma squared.
2 sigma squared is Rayleigh. We didn't cover Maxwell Boltzmann other than just mention it, but that's 3 sigma squared because it has 3 degrees of freedom. The degrees of freedom have to do with this. So anyway, so that means the expected value of I squared is equal to 2 sigma squared is equal to 16 over pi. And that means you got 4 pi times 16 over pi, or 64, and that units would be watts. You didn't get anything off if you didn't put the units in. That was part A. What's part B?
The probability that the power dissipated is less than or equal to 24 watts.
All right, but before I continue, I want to say one thing. You can actually go ahead, and if you want I squared there, because you have your calculus, you can go ahead and multiply this I. You get an I cubed over sigma times this, and you can do the integral with your calculus. Your calculators will do that integration, I believe, without a problem. But you got to set it up right, and that means you have to integrate this thing from 0 to infinity. But it will do it if you, I mean, literally, if you didn't think any other way to do it, you can do it that way. Okay, now we want the probability that the power is what?
Less than or equal to 24 watts.
Now, correct me if I'm wrong, but I think you got a density function for power. Am I right about that?
Yeah.
Yeah, I don't recall anybody else doing it. You could. Do you need to? Because effectively, what you can do is just back out the value of I, correct? So the probability that the power is less than 24 watts is the same thing. If you think about that, if you have 24 watts is equal to I squared R, that means I squared is equal to 24 over R, or I is equal to the square root of 24 over R, or I is equal to the square root of 24 over 4 pi, and frankly, I don't know what that is. Someone went through square root of 6 over pi. So this is the same thing as the probability that I is less than square root of 6 over pi, and that is going to be 1 minus exp to the minus, and then it's going to be I squared, so you get 6 over pi here, over 2 times sigma squared, or sigma, 8, 2 times 8 over pi. I'll get out of your way in a second, but I'm just writing this down. Complete this 1 minus exp to the minus 6 over 16. And first, do you all agree with what I'm doing here? I'm calculating the value of I. It has to, it's less than, I didn't do what he did, we get the density function for the power, but you can if you want, and I didn't ask for it for a reason, it's kind of messy. But for that one, what is it?
0.313.
Do y'all agree with that, class? I mean, is everybody with me on this? Just doing the mathematics. So that was that part. What's the next one?
Probability that the power dissipated is greater than 72 watts.
All right. I just erased what I made. So the probability is less. Well, let me do it this way. So power equals I squared R. And if it's 72 equals I squared R, that means I is equal to 72, or I should say, over R square root. And that's the square root of 72 over 4 pi. So what is that? Square root of 18 over pi, and I don't know what that is. But they want the probability that the power, or I should say, is greater than. So that's 1 minus exp to the minus I squared over 2 sigma squared. But it would be that subtracted from 1, so it's effectively going to be this. Let's put it right here. It's going to be exp to the minus 18 over pi divided by 2 times, and I erased my sigma squared.
8 over pi.
Yeah. Thank you. And that's going to be, you tell me if I'm wrong here, minus 18 over 16, is that right? What is this value?
0.325.
Anybody confirm or deny that? Is that, you guys get that? I think it's right, but I'm just looking for one more confidence. What'd you get? Oh, never mind. Put your test away, right? I think that's right. And does the answer match on the solutions post? Is that the right answer?
Yeah.
Okay. Is there another part?
No.
Okay, so that was the exam, and you know how to make them up, you know what I'm talking about. I take it from the homework, I don't think there's any problem about that. Let me do one thing and I'll let you go. Matter of fact, what I want to do is, we've had a lot of open time, basically. It's unfortunate because it kind of breaks up the flow of the class. I'm going to get into chapter 3, and I'm going to talk about some stuff. I put up a PowerPoint. Did you guys, can you see that on OneNote or not? Okay, that PowerPoint is Denny's PowerPoint. It's very good because it's really hitting the high points. And that last section where we had to look and estimate where the peak is in section 3-2, don't worry about that. What we're really talking about, when we're talking about this conditional probability, and we want to see if things are statistically independent or not. And I've got notes on this, but I'm going to do this. I'm going to just show the PowerPoint. I'll show you what the idea is, and we can apply it to problems. Yeah, it's been a while since we talked about this stuff, and I know how some of these things, they can confuse the crap out of me. And I'll try to be as clear as I can about this. If you want to, you can access the PowerPoint. You don't have to. I'll put up some stuff in it and use some problems. so we've done the joint density functions, and we've been through this. This is all section 3-1. I think y'all remember this when we had two variables, how you basically got either the probability or either density function of just x or just y out of there. Keep going through this. Those homeworks we did already. We run through 3-1.3. Now, this is the one part we were talking about, and he had a lot of estimates of finding the minimum or the maximum of these things, but there isn't, basically you're going to get a form of the integration. You have to take a look at where the maximum is when you're doing this, but let me get to this one. So really, when we talk about f of x, where y is known, or f of y, when x is known, either one, right here, you're really talking about finding the joint density and dividing it by a single density of either y or x. That's the whole crux of this thing. You have to be able to obtain that. The way you get it is integrate this right here over all possible values of x. Take a moment and listen to me. Y'all follow me on that, class? So basically, if you have f of x comma y, the joint density, you can always get f of y or f of x. And that's the key. So anytime you're asked for f of x given y, you need the density function for y to get that. It's really coming down to that. Now, anytime, once you have this conditional density, by the way, this is important what I'm about to say. Now, if you want the mean value of x, given that y is a certain value, then you have to take this density function, multiply by x, and do the integration. And vice versa, for y, you do the same. All right, Bayes' theorem. The only thing you're doing here is what we've done before. Instead of having the probability of y given x, now it's f, it's a density function of y given x, is the density function of x given y times f of y over f of x, and the total probabilities. Now this is important. You see how he has f of x comma y is k times x plus y? Anytime you have things that are statistically independent, you can always break f of x comma y into just the function of x and just the function of y, multiplied together. Do you hear me on that? I'm going to make my point some more in a second. This is real important. This one you can't separate. You have x plus y. You can't get two things that are multiplied together. Anyway, the value of k, how do you get that real quick?
Integrate it and set it equal to 1.
Integrate 2 times from 0 to 1 and x and y, set equal to 1 to solve for it. And lo and behold, k is 1, which is nice. All right, now the probability of x greater than half given y equal 1/4. Think about that just for a second. You can put it up and do it. Well, that's the joint density function, right? If we want f of x given y. Do you hear me on this? We want f of x given y. So what we need is f of y, correct? To get f of y, you would take that and integrate x from 0 to 1. Do you agree with that? And you're going to get what? X squared over 2, right? So, I mean, when you integrate this, then it's basically going to be 1/2 plus y, isn't it, class? Just do the integrations. So, given y is 1/4, let me show you. All right, so that's f of y, 1/2 plus y. Do you all agree with this? I know I'm going quick, but I'm trying to make a point. If I put this up on the board, it'd take an extra 5-10 minutes to get this done. You with me? And this is the exact thing that we just had up a second ago, 2 slides back. So the probability of x is the density function given y. It's f of xy, that's x plus y, divided by f of y, that's this. Now, that's an awkward looking thing, but in essence it's it. Now he says, given that y equals 1/4, hear me on this. Everybody got that? So if y equals 1/4, this is gonna be 1/2 plus 1/4, right? Or 3/4, right? And y here would be 1/4. So you have only a function of x you have to integrate. But he wants to know what x, the probability is x greater than half, so he's gonna show this. Now you see the 3/4 down here? The only thing we're doing is replacing y with the value 1/4. There's the 3/4. Y up here becomes 1/4. We're going to integrate that from 1/2 to 1, and that would be 2/3. Now that is pretty straightforward, but the key is getting this correct first, and then making the substitutions after you have that. Follow me, class? You have to do it that way. Now, the problem 3-2.2 we can do, but I wanted to get into the next section. I got about 15 minutes, but the reason I want to get in this next section, we should have covered it by now, but time didn't allow. So this is the thing I was mentioning, statistical independence. We can do 3-2.2, but I promise you it's not hard. If you just saw what I did there, it's not hard to apply that theory. Two random variables, x and y, are statistically independent if and only if. You see how you can separate f of x comma y, the joint density function, into just the function of x and just the function of y. This becomes real important with certain types of problems. I'm not going to say much about radar because I got to be careful. I'm not sure some of these things are truly statistically independent, but ground clutter is usually completely statistically independent from the radar cross-section of an object. So when you're getting a whole bunch of stuff back and you know there's noise there, usually you can separate out the clutter noise into a separate category and statistically get rid of it. Usually, but I got to be real careful because there's a thing called a multipath problem where you hit the object with a radar signature, then it hits the clutter, hits the ground, and scatters back, and then you have something where you can get something that is not, it is dependent, but that depends on the separation between the clutter and the aircraft. Okay, so basically, if they are statistically independent, this is real important right here, then f of x given y is just f of x. Y has no bearing on the outcome. Follow me? And about the same way, if this is true, if they are statistically independent, you can take a look. This f of xy becomes just a function of x times just a function of y, so the f of y's cancel. That's the idea behind this. All right, now, I get them from Circle K. I get them from, you know what I'm talking about, Circle K?
Mm-hmm. Dave & Buster's has been blowing my phone up.
They always send me something stupid. The random variables x and y are uncorrelated. There's a difference between statistically independent and uncorrelated, and it's a very slight difference. But if you can do this, the expected value of x times y is simply the expected value of x times the expected value of y. In other words, if the density functions are separable, think about it. If f of xy is separated into just f of x and just f of y, then the mean values have to be separable too. You follow me? Okay. So, before I go on, this is the first problem we looked at. Are they statistically independent? Can you get just a function of x times just a function of y looking at that density, joint density, class? No. Can't. They're not. So, how about this one? Sure. You could have f of x is 4x, f of y is y, they're separable, right? You can just multiply f of x and f of y and get that. Now, are they independent? Yes. Density functions that are separable are independent. And then here we go with the proof. You see how he's got x and y. If they're independent, then f of xy becomes f of x and f of y. And then you can take f of x times x and f of y times y and do the integrals separately, and lo and behold, you get x bar or y bar, or they are in fact. If they're statistically independent, the expected value of x is independent of the expected value of y. You can get them separately. But here's something that's a little interesting. Uncorrelated functions don't necessarily mean they're independent. And the real thing with with uncorrelated, the first and second order statistics have to be used to determine that. Independence is just density functions. Don't worry about that part. In information theory, I think probably in Dr. Tugnate's class in communications, he'll probably touch on some of this stuff. And the real thing is when you do signal transmission and there's information in it, and anytime any data stream correlates, is related to in some way, shape, or form another data stream, they're not independent. But he will go down this road with you, I'm sure. Okay, now for this one, I'm going to ask you. See, this is where we get to another level of complexity. I want you to take a look at this and tell me, I want your thoughts on this. Are they independent or aren't they independent? How would you prove it, or how would you go about either proving or disproving it? Well, let me ask you this. Can we get f of x out of that? Just the function of x. How would you get just the function of x from this density? Can you all see this okay? How would you do it?
Integrate for y.
Integrate out y, right? Integrate this function dy from 0 to 1, right? And you would get f of x. Could you get the f of y? You would integrate this out with x, right? Same thing. Now, if you multiplied f of x that you got times f of y, and you got this, guess what? They're statistically independent. You can separate f of x and f. If you can't do it. But if you take a closer look at this, maybe you can factor it. What if you have x plus 1 times y plus 1? I don't want to play around with these factoring problems too much. The integration is the easy way to do this. But you all see how this surely looks like there's a lot of similarity. There's a cross term, x and y. What if you have x plus 1 times y plus 1, or maybe y plus 2? Take a look at this. Can you see how multiplying those you could get that? Now let's take a look. Yes, x plus 1, y plus 2. They factor out that way. But even if you didn't know that, if you integrate those things and get an f of x and an f of y, and you multiply them together, you will see, in fact, you get that. Follow me, class? All right. And you're going to be asked something, you're going to be required to understand how to do a problem of this nature, this type of problem. And finding k, how would you find k? Well, there's one property you all know. What do you do? Integrate f of x comma y from 0 to 1, 0 to 1. And x and y, set it equal to 1 and solve for k. That's it in a nutshell. There's no tricks on this one. And lo and behold, there it is. There's k. Just a straightforward integration. Now what about the expected value of x and y? First, let me go back here. They're independent, correct? So here's a tip, and this is really handy on tests and quizzes, in my opinion. How would you find this based on what we just talked about?
Take the mean value of f of x and then the mean value of y and multiply them.
Right, and since we have just f of x, we can take x times just f of x and integrate it, and then take y times f of y and integrate it, right, from 0 to 1. Get those values and multiply them. That's exactly what you should do. And actually, the expected value of x is just, we're just doing it right here. And he's going to show you the expected value of y and multiply them together. And lo and behold, that's how you get it. Now, these kind of things, I want to just warn you about this. When I look at this, I see probable, I see mistakes because people go too quickly through that calculation. So take care when you're doing these things. It's easy to make stupid mistakes. Stupid mistakes hurt people in this class a lot. Really just oversight sometimes. Okay. We'll do problem 3-3.1 for homework. I'm surprised I got through that whole section. But of course, I don't like PowerPoints. I think they serve the purpose here because that stuff is not that hard. But you have to at least understand the concept of separation, being able to separate. By the way, I don't know any real quick tricks for factoring. I don't think your calculators have the ability to factor. They do. For symbolic factorization, X, Y, and Z. Well, they're a lot better than my calculator. Well, I'm glad they do. Because if you can do that, these problems are going to be cake, in my opinion. Now, I'm going to tell you one other thing we're going through. So I'm right at this point, I'm assuming we've covered section 3-2, even in, 3-2 and 3-3, even though, no, we didn't spend a lot of time doing a lot of problems, there aren't that many problems in these sections that are really pertinent to where we're going. They're just touching on the basic statistical independence thing. But with correlation, how many have heard of correlation before? What is it really in your own words? You've heard of convolution, right? What is when you convolve two things, what are you really doing? You're taking, if you have like, say H of t is an impulse response, right? And you have an input signal X of t. If you convolve X of t with H of t, you get the output Y of t, right? But what are you really doing? Well, you take X of tau and then H of t minus tau, and then integrate d tau from minus infinity to t. And really did you get the thing where you basically take one function, flip it, and then shift it over the other function, and the overall, the area that overlaps, you multiply point by point, you get here. That's called convolution. Correlation is the exact same thing, except you don't flip. Instead of taking one function and flipping it before you do the actual integration, you keep both, you don't flip either function. But what it does is this. It will tell you what relation one function has to the other in time. Now let me get your interest back. So why would that be important? Well, I can tell you one reason. It had a lot to do with my personal interests, and that's the stock market. Because stock prices, because of investors, follow discoveries. Right? They go up when there's a new discovery, and as time goes by, if there's not, they go down. There's basically, in a nutshell, kind of that. There's more to it. So take Intel, for instance. Well, when Intel created a new processor, their stock went up. And now it just happens. Then there are companies that use it, like Dell Computer. So about 3 or 4 months later, Dell Computer's stock goes up. Amazing. Almost predictable. It is predictable. So if you correlated the historic prices of Intel stock, and this is just one of many things that actually create computer parts, to Dell Computer, if you correlated, you would see that at the 4-month bound, and I don't know this for sure, speculative, 4 months, 6 months, in that range. All of a sudden, if Intel's price goes up, 4 months later, Dell's price. The correlation function lets you see that. You'll see spikes in the correlation function that tell you the time lag between one event and the next statistically. And that gives people who buy and sell stocks some insight. And we even made a program, a kid named Sungil Kim, brilliant kid, graduated MIT, he's finishing law school. He was here, he did his PhD at MIT. We wrote a paper on using a genetic algorithm to do basically that. And I wish I had more money to invest in that, because I could retire today. I can anyway. That's what correlation does. So it's not just a goofy function. This one makes money, and it also helps you forecast things very effectively. So what does correlation mean? It's a relationship between things. So they got shoe size on one and height on the other. Well, the bigger the foot, probably the bigger the kid. I mean, it's not exact, but This is what he's trying to show you. Then uncorrelation, shoe size and vision. You wouldn't think there would be any difference, right? I mean, any effect of one on the other, right? And surely there isn't. He's trying to show that. What about car weight and miles per gallon? Should have an inverse correlation. The heavier your car, the worse the mileage. And surely, can you see how it's a downward trend on here? Can you all see that? Okay. Yeah, he's trying to show you what these things, what you can see with correlation. And it's based on statistical data. You have a whole lot of data, and you got two or more variables that are affecting each other. You want to see how strong the effect is. And in the stock market, if you get an exact effect, now you can go to the bank and take a loan because you've got some reason to get bet on that one. It's pretty sure. All right, so I'm going to have to spend more time on covariance, but what we need to do is quantify the relationships. This is where correlation comes in. And I want to, normally what they do is subtract the mean value, if possible, from the data sets you have available. They always want to get it where the mean value doesn't skew anything. You're just going to have to go with it. It basically puts everything down so the change will be greatest about the zero axis. They get rid of the mean. Now, so I want you to just hear me for a second. First, I'm going to have to define correlation exactly. There's something called a correlation coefficient. And it's the expected value of, if you look at this, x minus x bar, y minus y bar, and they always normalize with sigma x, sigma y, and they get this. Now, I'm going to say one thing, just listen. See how he calls this a correlation coefficient? The closer that is to 1, the more correlated they are. But I want you to listen. Take a look with me right here. You see the expected value of xy? If they were statistically independent or uncorrelated, this would just be x bar times y bar. You all see that? X bar times y bar minus x bar times y bar is 0. The correlation coefficient is 0. So if things are completely uncorrelated or close to being completely uncorrelated, the correlation coefficient is 0. Now if something is highly correlated, then this value will be much different than this value. And that's what you want if you want to predict things. You're going to have to see how this works. First, I want to see where he defines better stop there. I'm over by 3 minutes. But I want to tell you this stuff with correlation. It's really very useful and interesting. And in my personal line of work with radar, I can't tell you how important it is if we're getting a data signature. Say we've got radar, and it's basically it's lighting up some target out there, and we're getting the echo return. And we take this and we strip out the high frequency. Think about bringing things through. Just think about your standard AM radio, stripping out the high frequency carrier, you get down to baseband, it's audio. Follow me? So you strip out the high frequency carrier of the radar signature, you get down to baseband go from A to D, and then you catalog all this information. Then we take that and we have data sets, and we know, statistically speaking, if we analyze this, if the statistics of the recorded signature align with this target 1, we know it's target 1, target 2, it's target 2, and we can identify even though we can't see the thing, but because we have a data record, we can catalog what that target is with a high degree of certainty. And that's what happens with a lot of this stuff. And we use correlation all the time. You can use convolution. It's basically the same thing, only it's a time reverse signature. But you have to have a data record of some length to use this. It's not something, they do what's called a running average. Have you heard of fast Fourier transforms? You know what that is? All right, with a fast Fourier transform, they're catching a signal and they're recording it to a certain length of time. They have a data record from the time the signal's coming back to maybe 15, maybe 30 milliseconds before that. They got a data record and it keeps on refreshing. They take that into a very fast Fourier transform and you can get the frequency spectrum. But it's continually changing and it's got to be updated all the time. It's the same way with correlations with anytime you're looking at real-time signatures. I'll spend more time on that But this is stuff I'm interested in, and you'll see, I'll try to get you interested in it too. Okay. Have a great July 4th, and if you are traveling, please drive safely. The police are going to be out in force, I can tell you. Anybody go down to the beach?
I'm going to the lake.
Martin?
Yes.
My, I may be going there.
I could go to the beach, but then I'd have to go home, and I'll be gone.
I bet you a lot of people are going to be down at the Gulf. I mean, a whole lot.
Yeah. So my thought was, well, everyone will be going down, so I'll go up.
Well, no, Martin's going to be loaded.
True.